Hello, everyone, and welcome to the CosKASI ECR seminar. It's a great pleasure for me to introduce our speaker, Joby Kochappan. Joby did his PhD degree at the Indian Institute of Astrophysics under the supervision of Parvati Chingampam, mainly working on statistical analysis of CMB data. Afterwards, he was a postdoc at the NISA Bhubaneswar, working with twin course. And he's now working with Stephen Appleby at the Asia Pacific Center for Theoretical Physics in Korea. So today he will share his research on search for statistical anisotropy in cosmological data using Minkowski tensors. So Joby, please start when you're ready.
Thank you, Oyan. Thank you, Oyan, for the introduction. I want to thank David and Kasi for giving me this opportunity to present my work in front of you guys. And so I'm currently working with Stephen Appleby at APCTP Pohang. And today I will be presenting some of my recent research, which I've done with Stephen and Prabha, who was my PhD supervisor, and Tuhin, who was my supervisor during my last postdoc, and Aparita and Somen, who are my collaborators from Isotropy. So I will be presenting two projects. So the first one is the application of the Minkowski tensors to CMB data. I did this during my first postdoc at NISA Bhubaneswar with Tuhin Ghosh. And the second project is their application to density fields in redshift space. So let me start with one. So we have the standard model of cosmology, which is the lambda CDM model. And one of the fundamental assumptions of this model is that the universe is statistically homogeneous and isotropic on large scales. It is important to test this assumption against observations. And we use the Minkowski tensors to test the statistical isotropy of the CMB data, specifically the temperature and E mode polarization maps. So for this purpose, we use the contour Minkowski tensor, and we'll shortly see why this is a suitable tool for measuring statistical isotropy of these maps. So the Minkowski tensors are tensor generalizations of the scalar Minkowski functionals like area fraction and boundary length and genus. The contour Minkowski tensor can be seen as the tensor generalization of the boundary length. So we'll see the definition in the next slide. And previously, we have applied the contour Minkowski tensor to the Planck temperature data, Planck 2018 temperature data, and we did not find any violation of statistical isotropy. Prabha and Vidya did an analysis using the Minkowski tensor, contour Minkowski tensor of the E mode data back in 2017. But at the time, they had to use stereographic projection to estimate the Minkowski tensors from the data. And they didn't have access to the SMICA simulations that we have today. So they had to compare the CMB maps with the individual frequency simulations, which is not an ideal comparison, but it was what was possible at that time. So now and they found a 4 sigma deviation from SI in the CMB E mode maps. So it's this 4 sigma deviation could possibly arise from the use of stereographic projections, or it could arise from the systematics being different for the 70 gigahertz simulations as compared to the CMB maps. So it's important to check these now that we have a way of calculating the Minkowski tensors directly on the sphere. And we have access to the CMB simulations by the SMICA pipeline. It's important to check this and see whether we get a similar result. Do we still find a violation of SI in the mode data? So that's what we do here. So before defining the contour Minkowski tensor, I need to introduce the concept of excursion sets. So if we have some random field U defined on the sphere, then we can choose a threshold nu, and we can if we cut the field at this threshold, then that gives us an excursion set which consists of connected regions and holes. And the boundaries of these connected regions and holes form closed curves. Now, for these closed curves, we can define the contour Minkowski tensor. So for a given curve, the curve C, the contour Minkowski tensor W1 is defined in this way. So it's integral over the closed curve, t hat cross t hat ds. So t hat is the unit tangent vector at each point on the curve, and the cross is the tensor product of two vectors, which is defined by this expression. So this is definition for the contour Minkowski tensor, which we denote as W1. So what we do is now this W1 is defined for one particular curve, right? What we are interested in is we are interested in studying the statistical isotropy of a field. So what we want is when we select a particular threshold, we have an excursion set consisting of many structures, and we want to be able to quantify the isotropy of the distribution of these curves. So this is just one curve, but you can imagine that if we have some fluctuating field here and we cut off the field at a particular threshold, then we'll get many such structures and many such closed curves for the boundaries of those structures. So what we do is we find the contour Minkowski tensor W1 for each of these closed curves. And then we want to find the average W1, which is the element by element average of W1 over all the structures. Then we define the alignment parameter alpha as the ratio of the two eigenvalues of W1 bar, right? And the ratio in such a way that it is the ratio of the smaller eigenvalue to the greater eigenvalue. And that is what we call alpha, which is the alignment parameter. So alpha, for a given set of structures, alpha measures essentially the isotropy of the distribution of the closed curves, which means that even if the individual curves are not isotropic, but but what about their orientation? Is there a preferred direction in their orientation? And that is what alpha measures. So I think that is easily explained. I think it's much better to look at this figure. So for a circle, it's just one figure. So if we just one structure. So if we calculate alpha, we get alpha is equal to 1. So which means that it is isotropic. So by construction, we can see here that by construction, the value of alpha is always between 0 and 1, because we choose the ratio of the smaller eigenvalue to the larger eigenvalue. So for a circle, the value of alpha is 1. Now, if you look at an ellipse, then the value of alpha is less than 1. It's somewhere between 0 and 1, depending on how elongated the ellipse is. Now, if we take a pair of identical ellipses, which are aligned, which have major axes that are aligned, then again we find that alpha is less than 1, which means that it is not isotropic. It is not isotropic. The set of curves is not isotropic in the sense that they are individually not isotropic, yes, and they are both aligned in the same direction. So there is a preferred direction of alignment, which is what is being reflected in alpha being not equal to 1. So it's saying that the set of structures is not isotropic. And we can look at another case where we have many identical ellipses, but they're all but their axes are all aligned in random directions. So there is no preferred direction for the alignment of these axes. So even if the individual curves are not isotropic, we say that the distribution has no preferred direction. There is no preferred direction of alignment in the distribution. And so the distribution is statistically isotropic. And so for this set of curves, alpha is equal to 1. So this is the information that alpha captures. It captures the information about the whether the we can think of it as the isotropy of the average curve. If we stack all these ellipses on top of each other, then we find some sort of an average curve based on radial distance from the center. Then we'll find that the resultant average curve will be rotationally symmetric. And that is what we mean by isotropic for alpha is equal to 1. This is the information that alpha is capturing. Right. So in order to calculate alpha numerically from a discretely sampled field, which is what we have in cosmological data. So if so if U is a discretely sampled field, then we first transform this. All right. So we have a line integral here. We transform the line integral to an area integral using a Jacobian, and that introduces Dirac delta. So this is the Dirac delta function, delta U minus nu t. U is the value of the field at the particular pixel, and nu t is a threshold. And U semicolon 1 and 2 are the covariant derivatives of the field along the coordinate axis. And this is the magnitude of the gradient of the field. So this is an integral over the area rather than over the boundary of the structures as previously given in this expression. So now we have an area integral, and the benefit of doing this is that if we discretize the Dirac delta function as in here, so then we can compute W1 bar as simply the sum over all pixels of this quantity. So it's much easier to compute than this one, this expression, which requires us to identify the boundaries and perform the integration on the boundary. Okay, so right, so this is how we can compute the integral numerically for a discretely sampled field. And the mean curvature kappa can be written in terms of the field derivatives. So the advantage of doing this is that we have written every single term in the integral in terms of the field and its derivatives. So now we can compute it numerically. So moving on to the data. So this is the SMICA E-mode map that we use. So it has a resolution of inside 128, and it is smoothed with Gaussian beam of 80 arc minutes. And this is the mask that we use. It's a binary mask, which is basically derived from the Planck recommended common polarization mask. And again, it has inside 128, and it has a sky fraction of about 78%. So the regions close to the galactic center have been removed from our analysis. If there are any questions at any point, please feel free to stop me. Yeah. Right. So right. So we know that the Planck E-mode maps are very noisy. So an important question is like, is our estimator capable of detecting the properties of the signal in a map which is extremely noisy? So we have the signal and we have a lot of noise. So can our technique pick up the statistical properties of the signal from map which contains both signal and noise? So to address this, we design a toy model where we use thermal dust maps provided by the Planck team, and we know that the thermal dust is not not isotropic. So that serves as a signal. So we have a signal that is not isotropic. And what we do is we add varying levels of statistically isotropic white noise. So what we want to do is start with maps where we have only the signal, and then gradually add more and more noise, and find out a level of noise where beyond which our technique is no longer capable of detecting the properties of the signal, right? So we can say that, okay, as long as the signal to noise is greater than some particular value, our technique can capture the properties of the signal in the maps. So the level of noise, we quantify it as the ratio of the RMS fluctuations of the signal and the noise. So in this case, RMS fluctuations of the thermal dust to RMS fluctuations of the added noise. And we call this ratio gamma. So a larger value of gamma means that there is signal is dominant, and a smaller value of gamma means that noise is dominant. So we start with high values of gamma and we move towards lower and lower values of gamma. All right. So in this figure, this is a visualization of the toy model maps. So on the left side, we have the toy maps, that is the anisotropic signal and added isotropic white noise of different levels. And on the right side, we have statistically isotropic simulations, which we generated using the same power spectrum as the corresponding maps on the left-hand side. So, the topmost map is one that contains only the signal and there is no noise. And as we move downwards, we keep adding more and more noise till the maps become very noisy and like completely noise dominated. Right. And we compute alpha from these set of maps and compare those with these set of maps, right, for different levels of gamma. So this is so these are the alpha values that we obtain. So the y-axis is alpha, the x-axis is the threshold nu, and the black dots are the alpha values from the toy model maps, that is the anisotropic signal plus isotropic noise. And the blue crosses are the alpha values from the simulations. So I think we use 1,000 statistically isotropic simulations here. So starting with no noise case, where we have only the signal, an isotropic signal, we can see that the map, we can see that the toy model maps are clearly anisotropic. So I explained how alpha being closer to 1 means reflects that the field is isotropic. And if the field is anisotropic, then you have some value between 0 and 1. So here we can see that the values of alpha are smaller than the median values for the isotropic simulations. So we can say that, okay, yes, these toy maps are not isotropic. Then we add some level of, we add a small quantity of noise, but the signal is still dominant in this case. So gamma is equal to 2. So again, we see that the toy model maps are not isotropic. And then we add even more noise so that gamma is equal to 1, so that the RMS fluctuation of the signal and RMS fluctuations of the noise are equal. And we find that at this point, yes, the alpha values from the toy model maps are somewhat in agreement with what we see from the median of the isotropic simulations. But there's a catch. We can see that even if they are in agreement within 1 sigma or 2 sigma, right, at each across all the thresholds, the alpha values for the toy model maps are consistently lower than the isotropic simulations. So what we can do is we can find a combined p-value estimate. Like, what is the likelihood of finding such a realization where these alpha values are consistently lower than the isotropic simulations across all the thresholds. So we do that, and we find that this is the probability of this happening is like less than 99.7%. So we can say that even at noise level of gamma is equal to 1, alpha is able to distinguish alpha is able to pick up the anisotropy of the signal even in the presence of noise. Now we add even more noise so that the RMS of the noise is twice that of the signal, and the resultant toy model maps are noise dominated. So we find that, and when we get compute the alpha values, we find that the toy model maps are now consistent with statistical isotropy, and our estimator alpha is not able to detect the anisotropy of the signal because there is so much noise. So what do we conclude from this? We conclude from this that for these toy model maps, as long as the level of noise is gamma is equal to or greater than 1, so the signal strength of the signal is greater than or equal to 1, then alpha is able to pick up the statistical properties of the signal even in the presence of noise, right? So moving on to the data, we find that in the SMICA database on the SMICA, so the SMICA team Planck team provides the SMICA observations, and they provide noise estimates from which we can estimate gamma for the data map. We find that gamma is slightly greater than 1 for the SMICA E-mode map. And so we can say that alpha, our estimator alpha, should be able to pick up if there is any anisotropy in the signal, our estimator should be able to pick that up. So we compute alpha numerically from the SMICA E-mode map and the SMICA CMB simulations, E-mode simulations. And again, the black dots represent the data, and the blue crosses represent the simulations. And we find that the data is consistent with the isotropic simulations. So we conclude that given that we know that alpha is able to detect the statistical anisotropy of the signal even in the presence of noise, as long as gamma is greater than or equal to 1, and gamma is greater than 1 for the data, and we find the resultant maps are consistent with statistical isotropy. So we conclude that the SMICA, the CMB E mode, we conclude that the CMB E mode is statistically isotropic. So that concludes the first project that I wanted to talk about. Are there any questions? Okay, so moving on to the second project. So in this work, we apply the Minkowski tensors to density fields in a redshift space. So so the peculiar velocities of the galaxies perturbs their apparent position in redshift space, and because of the Doppler boost, right? And but this effect acts only along the line of sight, and because of this, there is a global anisotropic signal because this effect does not affect the components perpendicular to the line of sight, but it only affects the components along the line of sight. So this induces a global anisotropic signal, and the Minkowski tensors are naturally suited to capture this redshift space distortion effect, because they are capable of capturing anisotropic signals in the random fields. So this is what we're going to do here. So there are two main effects when we talk about redshift space distortion. So the first is the finger of God effect, which arises due to the stochastic velocity of galaxies in bound clusters, such as bound structures, such as clusters. But this usually happens on small scales, and that's like a few megaparsec. The other effect is the Kaiser effect, which is the perturbation of the apparent position of galaxies in redshift space because of galaxies falling into a gravitational potential or an overdense region, or falling or moving away from an underdense region. So this is called the Kaiser effect, and we can see this, we can observe this at all scales. And in this work, we are going to focus mainly on the measurement of the Kaiser effect. Right. So coming to the definition of the Minkowski tensors. So similar to the previous work. Here we work with excursion sets, but in 3 dimensions instead of 2 dimensions. So the Minkowski tensor W0 to 1 is defined as the integral over the excursion set delta Q n hat square dA. N hat is the unit normal vector at each point on the excursion set boundary. And again, n hat square means n hat tensor product n hat, with tensor product being the same as what we defined previously. And W0 to 2 is defined as the integral over the excursion set. G2 is the mean curvature, and n hat square dA. And dA is the area element on the excursion set. And V is the volume enclosed by the excursion set. So if we so for an isotropic field, the diagonal elements of W102 and W202 W022 are equal, but we expect but if the field is not isotropic, then we will get different values for the diagonal elements, and we will use that to our advantage and measure the effect of redshift space distortion. Right. So in my previous work with Stephen and Prava and Changbo, we have calculated the ensemble average of Minkowski tensors in the plane parallel approximation. So what we do is we consider that the galaxies that we are observing are on a small patch on the sky, which is very far away from the observer. So what this does is that it allows us to assume a constant line of sight, which makes things simpler for us because we can just use a Cartesian coordinate system and align one of the coordinate axes with, we can align one of the coordinate axes with the line of sight, the common line of sight. There is just one line of sight. And that simplifies our calculation. So this gives us a redshift space field, which is homogeneous, but not isotropic. Not isotropic because the redshift space distortion effect acts along the line of sight. So it acts along one of the axes. In our case, we choose this to be the z-axis. So this induces an anisotropy. Right. So Kaiser calculated the relation between the power spectrum of the density field in real space and in redshift space for this kind of a setup, and the relation between the power spectrum is given as this. So PS is the power spectrum for the redshift space field, and PR is the power spectrum for the density field in real space, and beta is the redshift space distortion parameter, which is simply the ratio of the growth factor F and the galaxy bias B. And mu is the cosine of the angle between K, between the K vector and the line of sight. So because we assume that the galaxies are on a small patch far away, and so there is a constant line of sight. So the line of sight is a constant. So mu simply becomes K hat dot a constant unit vector, which makes our calculations easier. Right. So this is what we did in our previous work. So then we calculated the expectation values for W021 and W022 for an isotropic Gaussian field subject to redshift space distortion effect given by this Kaiser formula. Right. So we found that the amplitude of the line of sight component, so in our case, the amplitude of the ZZ component is enhanced as compared to the amplitude of the components perpendicular to the line of sight. So that is the XX and YY components. And we also find that the ratio of these components depends only on the redshift space distortion parameter beta. So the ratio of the components depends only on beta. And so if we can measure this effect from observations, then that can directly give us a constraint on beta. So that is kind of what we are aiming at. And we also find that W021 gives a tighter constraint on beta than W022. So we focus on W021 in this work for two main reasons. One being that it is expected to give tighter constraints. And the other being that W022 is, the calculations are extremely tedious, so tedious, in fact, that if I were to put the results here in the slides, only the results would occupy around maybe 20 to 30 slides. So it's maybe not worth putting in here. So, but if anyone is interested, then you can read it in our paper, which we will hopefully put out soon. So yes, so we will focus on W021 now, 021 now. And so now we want to calculate the ensemble average for W021, this one, without using the plane parallel approximation. So we say that, okay, the galaxies are distributed around us, and we can no longer say that there is a common line of sight. So the plane parallel approximation does not work. But we can notice that again the redshift space distortion effect is along the line of sight, and the line of sight is radially outwards from the observer. So which means that if we choose a spherical coordinate system, then the line of sight is always aligned with the radial direction. So this is very convenient because similar to the previous work, we have the line of sight aligned along with one of the coordinate axes, and that can make our calculation simpler. So right, so in such a case, the redshift space distortion operator is given by this expression. So delta is the density field in real space. Delta tilde is the density field in redshift space. Beta is the redshift space distortion parameter, and these are the derivatives with respect to the radial coordinate. And this is nabla raised to -2. This is the inverse Laplacian. So once we have the real space field, we can apply this operator to get the redshift space field. Right. So going back to the definition of going back to the definition of W021, we have an integral over the excursion set n hat squared dA. And we can again change the area integral to a volume integral and using a Jacobian, and that introduces a Dirac delta function, delta D. And we write down n hat in terms of the gradient of the field. So now the entire integrand is in terms of the field and its derivative. So delta I, delta J are the derivatives of the field. Delta J is basically delta I contracted with the metric tensor Gij. So right. So now this is another way to write the Minkowski tensor W021, and we can see that it is the volume integral of this quantity Wij, which is again we can write in terms of the field and its derivatives delta I delta J by magnitude of nabla delta and the Dirac delta. So what we do, the goal of this exercise is to calculate the ensemble average of Wij and the volume average of Wij, and to discuss when we can compare these two, whether the ensemble average and the volume average are equal or they're not going to be equal. So that's what we're going to do. Right. So starting with the ensemble average, I'm just going to say. Right. So starting with the ensemble average, we have the real space field delta R, And we can expand it in terms of the, we split it in terms of the radial components and the angular components. So the spherical Bessel functions, JL, and the spherical harmonics, YLM. Right? And we substitute this delta R into this equation, this one, right? We plug this in, delta R here, and that gives us a redshift, a density field in spherical redshift space. Right. And when we do that, we use the orthogonality properties of the spherical Bessel functions and the spherical harmonics, and that gives us the these expectation values. So these are the cumulants of the field. So delta tilde, delta tilde, delta tilde R, delta tilde R, and phi phi, and theta theta. Right. So we can, what we find is that the first term in each expression, in each of the cumulants, the first term is the same as what we find in the plane parallel limit. So this kind of verifies the plane parallel result. And we also find that there are additional terms. We can view these additional terms as corrections to the plane parallel limit. And these correction terms fall off as 1 over R square and 1 over R raised to 4. So for cosmological observations, R is very large. So these terms are going to be negligible. And for practical purposes, we can say that the plane parallel limit is more than sufficient. So the cross terms R theta, R phi, and other cross terms are all 0, except for one term, that is delta tilde R, and that is given by this expression. It depends on 1 over R cube. So an interesting point to note here is that the cumulants are now position dependent, which means the ensemble average, when you compute the ensemble average, this quantity is going to depend on where you estimate this quantity. So ensemble average at a particular value of R will be different from the ensemble average at a different value of R. So it is now dependent on the coordinates. All right. So
about 5 minutes.
5 minutes?
Yeah.
Okay. I'll try to wind up. So, so the ensemble average can be written as an integral in the probability space over all the variables. So here D is delta tilde and delta tilde R. And we know sigma is the covariance matrix of these variables. And we know that because of the symmetry of the redshift space distorted field, we know that it is statistically isotropic on the 2-sphere. So we can just condense the theta and phi component into one variable, which is what we do. We call it Y. And we have this expression for the probability density. And we can integrate this quantity numerically, and we can get ensemble average for Wij. So this this is the ensemble average Wij in spherical redshift space. Right. And so the solid lines represent the line of sight component, RR component, and the dashed line represent the perpendicular component. So that is theta and phi components. So yellow line represents the case for when the distance R is 10 megaparsec. So this is 10 megaparsec RR component, and this is the 10 megaparsec theta phi component. And similarly, R is equal to 25 megaparsec and 50 megaparsec. And for the plane parallel limit, we use a large value of R. Arbitrarily, we set it to 1000 megaparsec. So that is the gray line. So this is the plane parallel RR, and these are the plane parallel theta and phi components. Right. So we can see that the theta and phi components for R equal to 10 megaparsec seem a little interesting for these threshold values, but that could just be maybe we shouldn't be too hasty about drawing physical conclusions from that, because that could just be because we're using a smoothing scale of 20 megaparsec, and this is R of 10 megaparsec, so that could just be numerical error. All right. So we did the ensemble average. Now moving on to the volume average, we want to compute the volume average from simulations. So we use two main types of simulations. So the first is Gaussian random fields, and the second is the non-Gaussian dark matter simulations, that is the QRT simulations. So for the Gaussian random fields, we start with generating a homogeneous and isotropic field in a box. We smooth the field with Gaussian kernel, and we apply the plane parallel. We apply the plane parallel redshift space distortion operator and the spherical redshift space distortion operator to get the plane parallel and spherical redshift space distorted density fields. And similarly, for the dark matter simulations, we take 50 realizations from redshift 0 from the curated simulations, and we smooth them with a Gaussian kernel. And we generate the plane parallel and redshift space fields by perturbing the particle positions in the plane parallel case along the z-axis by this expression, and perturbing the particle positions along the radial direction by this expression for the spherical redshift case. So now, we can write Wij for a given pixel for a discretely sampled field, and that is given by this expression. And the Dirac delta can be discretized similar to what we did in the previous work. Right. Sorry. So the normal vectors that we use for in the definition of the W021, these normal vectors belong to the tangent space at each point on the excursion set. So we cannot blindly take a sum over these vectors or these quantities which belong to different vector spaces. If we want to perform this integral or this sum for the case of the discrete field, then we first need to parallel transport these vectors, n hat vectors. We need to parallel transport them to a common point, and then we can perform the integral at that point. So which is what we do. So because we know that our field has a spherical symmetry, we choose spherical coordinate system, and we use great arc parallel transport, which is the geodesic on the two sphere, followed by a radial translation. All right. So this gives us two expressions for the volume average of Wij in for the real space field and for the spherical redshift space field. Here, gamma denotes the parallel transport along great arc for the vectors from the pixel M and P to a common pixel. So we can expand the Wij volume average Wij in the Hermite polynomials, and we call the coefficient of the first Hermite polynomial as the amplitude of Wij. For a Gaussian random field, we expect that the coefficients of higher order Hermite polynomials would be 0. So we refer to this as the amplitude. And now we can take a look at the results. Is it okay if I take like 5 more minutes, Boyan? I think these are final few slides. Yeah. I will conclude very soon. Yeah. Thank you. So so these are the volume average for Wij in redshift space and in real space. So so the diamonds represent redshift space and the dots represent real space. So the red dots, red diamonds here are the line of sight component in redshift space, and the blue and green diamonds are the perpendicular components in redshift space. And these dots are the components in real space. And we can see that the amplitude of the line of sight component in redshift space is enhanced, and the amplitude of the perpendicular components is lower than lower in redshift space than the real space. And similarly, we present the amplitude Aij against the smoothing scale RG. So again, the red diamonds are the line of sight component in redshift space, and these are the perpendicular components. The golden solid line is the plane parallel Kaiser limit, and golden line of sight component, and the golden dashed line is the plane parallel Kaiser limit for the perpendicular components. And the silver line is the isotropic, are the AIJ for the isotropic case, which agree well with what we find in real space. And I will skip through some of these contents. So we also compute the coefficients of higher order harmonic polynomials. So A1 is the coefficient of H1 and A2 is the coefficient of H2. And we rescale the threshold to from nu to nu s so as to match the volume fraction of a corresponding Gaussian field. And these are the volume average. I think I have 2 or 3 more slides. Yeah, I think it should be okay. So these are the volume average of Wij in spherical redshift space. So red, these are the line of sight components, and green and blue, these are the perpendicular components. This is in threshold nu, but after we rescale the threshold to Gaussianize the statistics, this is what we find. And this is the same, basically the same quantity on the y-axis, the volume average, versus the rescaled threshold nu. For the diagonal components RR, theta, theta, and phi, phi. And we find that the off-diagonal components are consistent with 0. However, when we do the volume average in Cartesian coordinates, so it's important to note that in Cartesian coordinates, we simply add the components. When we add the components, we are implicitly assuming Euclidean transport, which does not respect the symmetry of the field. So because of that, when we take the volume average, the redshift space distortion signal, which is along the line of sight, it gets washed out when we take a volume average over all the directions. So the signal is washed out, which is what we can see here. So all the components are equal and agree with the isotropic case. Right, and I think, yeah, so this is the volume average, which we get, volume average on y-axis and smoothing scale on the x-axis. Volume average, the amplitude of the volume average for the dark matter simulations, QAT dark matter simulations. And this is the red diamonds are the line of sight components in redshift space. And the golden line is the Kaiser limit. We find that these are significantly different from the Kaiser limit. And we said this is because of the finger of God effect, which becomes important at small scales. And we can see that as we smooth at larger and larger scales, this difference dies down. And, the perpendicular components agree well with the plane parallel limit for a Gaussian field. And this is the ratio of the amplitudes for amplitudes of volume average for the dark matter simulations to that of a corresponding Gaussian field. And again, we find that while the theta, and phi components are also somewhat different, but they do agree with the Kaiser limit. But the RR component is significantly different and especially pronounced at small scales. And we believe this is due to the finger of God effect. And these are the higher order coefficients, so coefficients of H1 and H2. And we see that they are consistent with 0, but we can see that it is still some large values of A2 are present due to the finger of God effect. So to conclude, we have calculated the ensemble average of W of the Minkowski tensor in redshift space generally without using the plane parallel approximation. We find that unlike the plane parallel approximation, in this case, the ensemble average is position dependent, and so it is not recommended to do a naive comparison of the ensemble average with the volume average, because they will generally not be equal to 0. They can be 0. They can be equal, but that depends on the choice of coordinate system and the parallel transport that we use. If the parallel transport that we use is suitable for the properties of the field, then we can compare the ensemble average and the volume average. And for the QoT simulations, the line of sight component does not agree with the Kaiser limit because of the finger of God effect. So possible future work is we want to apply our technique to galaxy survey data. So like the BOSS survey, and constrain beta using our method. And another challenging work would be to construct a test of the statistical homogeneity of random fields using Minkowski tensors. So thank you for your attention.
Thank you for a really interesting talk. Are there any questions? While people come up with questions, I have a couple of questions myself.
Mm-hmm.
So yeah, these Minkowski tensor statistics are really interesting. I'm struggling to get a good intuition of them. So I was mainly wondering what the distribution of these statistics, like alpha, which is like a ratio of eigenvalues of this contour integral from excursion set.
You mean this one?
Yeah. So like if we think about the distribution of the alpha, or like later in your second part, like this Wij, if we look at the distribution for Gaussian random fields, would that still be Gaussian?
So the distribution of alpha is not Gaussian; it is a beta distribution, and
right.
And for Wij, you can find yes, the distribution is Gaussian.
Right, and okay, and would they be correlated at all for different values of new excursion parameter?
So we did that calculation for alpha, and we find that that depends on the field. So if we take if we generate like 1,000 realizations of some isotropic field, and we find the correlation between alpha across the different thresholds, we find that they are not correlated. They are not correlated. But
right.
it can be correlated if, depending on the field. Like if the field is moved to some angle, then yes, it can be correlated.
Right. Yeah, because I was interested in the joint p-value statistics you mentioned.
Yes.
I guess like if the distribution is Gaussian or not, and also if the correlates or not, be quite important.
So the correlation between the different alpha values at different thresholds is input for the combined p-value.
Right. I see. Yeah. Oh, I see one question from Sat.
Hi, nice talk. So I had this question for this particular figure. I can understand why your blue dots are not reaching 1, because 1 is the ceiling. But how far it is from the one ceiling, it depends on the simulation, means the discrete data.
Yes. So so I said that alpha should be equal to 1 for isotropic maps, right? But that's never really going to happen when we do when we compute it numerically for multiple regions. First of all, we don't have a continuous field, and there is also a discretization error that comes due to discretizing delta, the Dirac delta. There is an error that comes in due to that as well. So because of, and we choose to label the eigenvalues as lambda1 and lambda2 in a very particular way, right? We call the smaller eigenvalue lambda1 and the larger eigenvalue lambda2. So we are defining it in a very particular way. So because of this, all these three things combined, alpha will never be 1. It will always be smaller than 1. There are additional factors such as smoothing. So when we smooth the maps, it kind of washes out some of the structures in the field, right? It washes out some of the structures. And because of that, there are fewer structures to average over. So when there are fewer structures to average over, there is a greater statistical error. And that statistical error is systematically shows up as lower alpha values.
Okay, the next thing is that, but there should be a theoretical reason that why when you increase your threshold, your new, it just comes down. Do you have any intuitive picture for that?
I mean, I can make a hand waving argument, but basically, again, as you go to, so we're looking at Gaussian random fields. And when we are, this is not Gaussian, but when we are looking at random fields or Gaussian or Rayleigh, when we are looking at extreme values of threshold, I forgot to mention that what we do is we first subtract the mean from the field and we divide by the variance. So the excursion set, how we get the excursion set is by selecting a threshold value and we cut off the field at that value. So when we cut off the field at a very high value, right? We cut off the field as maybe 2 sigma, right? So then there are very few structures about 2 sigma. Or if we look at cutting the field off at -2 sigma, for example, and we find how many structures are there below -2 sigma, then there are very few structures. As compared to if we look at, say, cutting the field off at -1 or +1 or some other value in between. So there are much fewer structures at the extreme thresholds, which results in higher error, numerical error. And we expect that this will, higher numerical error will mean that we'll get a much lower value of alpha than 1.
Yeah, I'm actually unsure about your last statement. I could understand that fewer structure will give rise to larger error bars, but why it systematically brings down the value of the mean value of alpha?
Because how we choose to label alpha, right? We choose it as lambda 1 by lambda 2. If it was arbitrary, if it was just one eigenvalue by the other, then yes, we would expect that it should maybe stay the same way. But this is a systematic way of defining the alignment parameter, right? Smaller by larger. So whatever is the numerical error will always propagate in one direction. Does that make sense?
Okay, let me think more about this. Okay, that would be, and maybe go back to your previous slide. Yes, so here the definition, okay, I worked on the 3D part of it, not the tensorial, but the scalar one. But is it very close to the extrinsic curvature of or do you recall that this definition is very close to the extrinsic curvature or not? I mean, I'm just guessing here. I'm just thinking aloud.
So the extrinsic curvature is the derivative of the unit tangent, right?
Yes, on the surface.
Right. So
it's not
somewhat similar, but yeah, I would say somewhat similar. Yes.
Okay. Okay. Yeah, I'm done. Thank you.
Oh, okay. Thank you.
It's 5 p.m. So maybe we can have extra questions separately. But yeah, let's thank Joby again for giving a interesting talk. And